All right, let's learn about probability of events. We got two goals today: determine whether two events are independent or not, and determine the probability of dependent and independent events. So two events are independent if and only if knowing one outcome has no effect on the probability of the other. Both situations are doing their own thing and it doesn't depend at all on the other. Dependent obviously does. So dependent events exist if and only if knowing one outcome has an effect on the probability of the other event. Let's practice a little bit to help you understand. We're going to determine whether the events are independent or dependent. And in this unit, you're often going to see that verbiage not independent. Well, that means the same thing as dependent. Two six-sided number cubes, die, showing the numbers 1 through 6 are rolled. The first number cube shows a 6, and the second number cube shows a 6. Independent or not? These are independent. These are two separate die being rolled. One can land on whatever it lands on, and so can the other. It does not at all depend on the other. This is just a coincidence that they both landed on 6s. Juan and Carl, two equally strong runners run in a race, and Juan wins the race. Independent or not? Well, these are actually dependent because doesn't Carl winning the race depend on if Juan wins the race or not, and vice versa? Yeah. So those are dependent. They cannot both win the race. One outcome definitely affects the other. What about these? A little more practice for you. See how you do. Okay, rolling a die multiple times. You're rolling the same die over and over and over. Nothing else is happening, so it doesn't depend on anything. Picking marbles out of a bag with replacement. Anytime you see the words with replacement, that is automatically independent because nothing is changing. You pick the marble out, you put it back, same probability of picking whatever it is you want to pick. Picking pennies from a jar of change without replacement. Anytime you see the words without replacement, that means dependent. The probability is changing, right? Because you're taking that penny out, you're not putting it back. So no matter if you want to pick a quarter, penny, a dime, a nickel next, the chances of picking one of those has changed. For example, if you picked a penny out, the probability of picking another penny is now less, right? And the probability of picking a different coin is now more. Now that we understand that, let's just look at the general equation for a probability of any event. So any probability is equal to the number of favorable outcomes, so what you want to happen, out of the total number of outcomes. When A and B are independent events, then the probability of A and B is equal to them multiplied together. This is super important. You will need it on the part 2 test, so write it down. A spinner is spun twice. Determine the probability of first spinning an even number, and then spinning in the number 1. Okay, are these independent events? Absolutely, right? You're just spinning the same spinner over and over. So the probability of first spinning an even number times the probability of then spinning the number 1. Well, what does that give us? Even numbers, I see 2. That's the favorable outcome out of total. There's 4 outcomes on the spinner times probability of 1. Well, there's only one 1 there, isn't there? So we simplify this to get 2/16 or 1/8. Let's practice some more. Use the given scenario to answer the questions. On a true or false quiz of 5 questions, Jorge guesses at each answer. Jorge should have studied a bit, I'd say. What's the probability that A, he gets a perfect score? Let's focus there first. A perfect score, well, we can already imagine that probability will be pretty low, right? Let's think about this. A true or false quiz of 5 questions. So what are the events? Answering a question, right? So we could say the probability of getting 5 correct is equal to the probability of first getting number 1 correct. I'm just going to put a C for short, right? And the probability of the next event, getting number 2 correct, and so on, right? Are these independent events? Yes. He can answer whatever he wants on any question, so we're going to multiply all these together. So this would continue on, probability times of number 3, 4, and 5 correct. So the question becomes, what is the probability of getting a true or false question correct? Well, that's going to be 1/2 times 1/2, and there are 5 questions. The probability every time is 1/2. We multiply all of those together, we get 1/32. So again, this is using this logic that if 2 events are independent, then the probability of them both happening is equal to their probabilities multiplied together. So B, he answers, we want to know the probability now that he answers the first 3 questions correctly. We don't care about the other 2. Well, that's the same thing we just did, just less of it, right? We're just talking about these 3. So if we multiply those together, probability of 3 correct, we're multiplying those 3 together to get 1/8. Notice how rapidly the probabilities change. Do you think he should have studied? I'd say so, because the probability of getting all 5 correct is very, very low. If you divide that, that is 3.1%. Very low chance of getting all of them right. Probably getting 3 correct, well, that's 1/8. That is much better. Still not great, but 12.5%. There's the notations all written out for you. That's exactly what I just mentioned, just a little more visual. And now let's look at another example where DeAndre has 8 shirts in a drawer. 3 are blue, 2 are white, the rest are red. Without looking, he grabs a t-shirt. He's feeling spontaneous. He grabs a t-shirt from the drawer, says, that's what I'm going to wear. Oh, maybe not. He puts it back. Then he grabs another t-shirt from the drawer. What's the probability of that? Both shirts he grabbed were blue. Interesting. Are these independent events? Yes, because why? He put it back, right? With replacement, puts it back. So we want to know the probability that what? Both shirts were blue. So blue, these are independent. So we multiply times probability of blue. So what is the probability of picking a blue shirt? Well, we know there are 3 blue. So there's 3, but how many total? 8. So favorable outcomes over total possible outcomes. Multiply those together, we get 9/64. Again, a low probability, and that makes sense. He's got different shirts with different colors. not very likely to happen twice in a row. Now, what's the probability that neither shirt is red? So these are still independent events. So we're going to put probability that it's not red times the probability that it's not red. And what is that? Not red is going to be blue and white. So that is 5 eighths times 5 eighths, 25 64ths. That's a much better probability. Close to 1/2. Okay. Moving right along. When the outcome of the second event is affected by the outcome of the first event, then the probability of A and B really means the probability of A then B. Okay? So pay attention because it's going to get a little wordy here. Basically, if events A and B are not independent, then the probability of A then B happening is equal to the probability of A happening times the probability of B after A. I know, a little confusing, but let's solve a problem to make it make more sense. A bag of coins contains 4 quarters, 6 dimes, and 2 pennies. Determine the probability of drawing a dime and then a quarter without replacement. Okay, these are what kind of events? Dependent. Dependent events. Okay, that's what we're talking about, not independent. Okay, drawing a dime, then a quarter. So that would be drawing a dime, then a quarter. Event A, then event B is equal to this. So the probability of doing what first? Drawing a dime times the probability of drawing a quarter then after we drew a dime, right? So what are those probabilities? A dime, they told us there are 6. Add up all the coins, you'll see there are 12. Okay. So what happened? A dime was pulled out, not put back. Then a quarter. So how many quarters are left in the bag? 4. We did not take out any, but how many coins are left in the bag? Be very careful. We didn't put that dime back. There are 11. And that is how you calculate probability for dependent events. Okay? Now we can simplify, cross cancel. 4 goes into 4 once, 12 3 times to give us 6 33rds. That can be simplified even more to 2 11ths. All right. So, to recap, if events A and B are independent, then the probability of both things happening is equal to both of their probabilities multiplied together. That's if they're independent. If events A and B are dependent, then the probability of both things happening is equal to this. We just worked this out. Okay? Basically, what this is saying over here to kind of clarify that notation there, the probability of A happening is being multiplied the probability of B happening given that A already happened. If that did more confusion than not, then just ignore it. As you're practicing these, it will get easier. Okay? So the probability of B happening given A already happened is the conditional probability of event B or the probability of event B given that A already occurred. That's what this line means. The probability of B happening given A already happened. That's what that vertical line tells us. And now that we have that information, let's practice some more. Wilma, Xavier, Yolanda, and Zane run a race. They're all equally good runners. What's the probability that Zane finishes first and Wilma finishes second? Okay, the probability that Zane finishes first and Wilma finishes second. How do you write that? Maybe just practice the notation for now. Are those independent or dependent events? Well, if Zane finishes first, Wilma can't finish first, right? So these are dependent. So we're going to multiply times the probability of Wilma finishing second, given that Zane already finished first. So let's work it out. Probability of Zane finishing first. How many Zanes are there? There's one. How many racers? 4. We're multiplying. Probability of Wilma finishing second. How many Wilmas are there? 1. Okay. But if Zane finished first, how many racers are now in the running to possibly end second? Only 3. You see how that notation makes sense? The probability that Wilma second, given Zane already finished first, that changes the denominator. Okay, so we multiply these together, 1/12. Okay, another one. Yolanda finishes first. So probability that Yolanda finishes first. Xavier finishes second. And Wilma finishes third. Okay, there's a lot going on here. So once again, these are dependent events, absolutely. So the probability that Yolanda finishes first times the probability that Xavier finishes second, okay, given that what already happened? Yolanda already finished first, right? There's 3 events happening, so we're multiplying 3 things together. The probability now that Wilma finishes third, given that what? Yolanda finishes first and Wilma finishes third. Okay, a lot going on here, but I think you will become more comfortable with this very soon. Here we go. Probability of Yolanda finishing first, we already figured that out. That's 1/4. Probability that Xavier finishes second, giving Yolanda finish first. Well, once again, there's only one Xavier, and if Yolanda finished first, there's only 3 runners left in the race. Okay, times our third probability. This one looks complicated, but it's not as complicated as you might think. Let's see. The probability that Wilma finishes third. There is 1 Wilma. Given Yolanda finished first, so that means we're down 1 racer. And who was this? Let me see. Yolanda finishes first. Xavier finishes second, given Yolanda finished first. And Wilma finishes third, given Yolanda finished first. And Xavier, this was wrong. Xavier finishes second. There we go. Sorry for the confusion. So Xavier would now be out of the running, right? If Yolanda finished first, Xavier finished second, how many runners are left? There's only 2 left. So that means Wilma has a pretty good chance at finishing third then, 50% chance. Multiply this all together to get 1/24. Conditional probability, meaning things depend on other things, right? Prime example here with the race. Okay. You've learned everything you need to learn today. Now it's time to practice. Corey's picking cards from a standard deck without replacement. Do you know how many cards are in a deck of cards? 52. Without replacement, keywords there. Find the probability of each event. Express your answer as a percent rounded to 6 decimal places. See if you can figure this one out. The probability of picking 4 10s in a row. Okay, let's see. Well, this is a favorable outcome, 4 10s. Out of total number of cards, I told you is 52. Times what? Well, if you're picking the 10, you're not putting it back, right? It says here, without replacement. So what do we multiply? There's now 3 10s out of 51 cards. There's now 2 out of 50. And finally, there's 1 out of 49. Multiply those all together, you get a giant denominator of 6,497,400. Divide that to get the decimal of 0.000004. That's 5 zeros to be exact. And they want this rounded, they want this as a percent. So percent means move your decimal 2 places to the right. Boom, boom. So now there's 3 zeros, 0.0004%. Rounded 6 decimal places, we have 4, so we are good. Okay. Find the probability that picking 3 hearts in a row from a deck of cards and assume replacement for this one. Picking 3 hearts in a row. But there is replacement, very key difference in solving. So we have probability that you pick a heart. Well, these are independent events, so you're just multiplying them together like this. I think we could all agree with replacement is a little easier, right? So hearts, how many hearts? Well, a deck of cards has 52. In order to find out how many hearts, you need to know how many suits, like hearts, spades, and diamonds, etc. So how many? 52 divided by 4 is 52 divided by 4. There's 13 of each suit. Okay, and that is not changing. These are independent. Nothing changes. Multiply together to get a large numerator and an even larger denominator. And that simplifies to 1/64. Okay. Let's do one final problem today. A youth soccer team consists of 15 players, and this is a list of the players' names. Suppose the coach randomly selects one player, randomly selects one player to set up pylons for practice. The coach then selects a different player to retrieve. I'm not going to highlight all of that, just the key part. Then selects a different player to retrieve the rest of the equipment from the storage shed. What's the probability that the players selected both have names that begin with the letter G? express your answer as a simplified fraction. This is a good question as an exit ticket for you to practice. Okay, let's see. So notation goes a long way in helping kind of think about what you're going to solve. We want the probability of first selecting someone whose names begins with the letter G. We'll call them G sub 1 since there's two of them. Now, are these independent or dependent events? These are dependent, right? He's picking different players. So if he picks this player here to retrieve the rest of the equipment, he can't assign this player to set up the pylons. These are dependent events, okay? So we need to multiply times the probability of picking a second player whose name also starts with the letter G, given that you already picked the first player whose name starts with the letter G. So first, let's handle this order of business. Probability of selecting someone whose name starts with G. There are one, two, only two. Okay. All right, so that's simple. 2 out of, they told us, 15 players, times the probability of picking a second player whose name starts with a G. Well, there's only one more player left whose name starts with a G. And since the first player is busy setting up those pylons, there's only 14 players left. So that's how we set that up. Multiply across, you get 2 over 210, which gives us 1 over 105. Very, very low probability. And that's it for today. Until next time, take care.